as I said, the next example has more to it. The reason there's more to it is you'll see by the number of critical points. But it's also a find and classify example. So find and classify the all critical points of, and the function f of xy again is 3x squared y plus y cubed minus 3x squared minus 3y squared plus 2. So two steps. Step 1, find critical point. So find critical point by, let's set the gradient to equal 0. So the partial derivative with respect to x, you get 6xy. The derivative of y cubed is 0, and here we have minus 6x, and everything is 0. And the partial with respect to y will be 3x squared plus 3y squared, and 0 here minus 6y. Okay? Alright. And we know ahead of time that we need to classify this thing. I tell you what, let's classify it later on. Let's find first the critical numbers, the critical points. So we want del f del x to equal 0. So we factor 6x, and we have y minus 1, and we're going to say this is equal to 0. And therefore we have two solutions here. Right? So we have one solution is x equals 0, and the other is y equals 1. So keep that in mind. We let f sub y to equal 0, and therefore we'll have 3x squared plus 3y squared minus 6y equals 0. So what should I do in this case? Well, I'm going to try x equals 0 and I'll try y equals 1 and see if I can come up with the solution. Because I'm still having one equation in two variables, so very little I can accomplish with this equation. So, well, let's try first x equals 0. Plug x equals 0, and therefore we lose the 0 term, and we can factor 3y. So we have 3y times y minus 2 equals 0. Well, this has 2y solution. Y equals either 0 or 2. So we have two critical numbers, two critical points out of it. Remember, x still equals 0. So xy going to be either 0, 0 or 0, 2. Okay? And now I'm going to plug y equals 1 in there. When y equals 1, then I'm plugging it in the del f del y. So I have 3x squared plus 3 times 1 squared, or 3 minus 6 equals 0, or 3x squared minus 3 equals 0, or x squared equals 1, and therefore x equals plus minus 1. So here we have the following. We have 2 points, either x equals 1, y equals 1 all the time, and the other is x equals negative 1 and y equals 1. So we end up having 4 critical points. So what are those? Gonna pay, you need to pay Juan because he's doing all this work for you.
Is it good?
I'll make sure they
Is it good?
That's great.
Thank you. So now we need to classify. Juan, will you be able to catch up with all of this while you're working on behalf of Roberto? Roberto has changed his name to Robert, by the way. Right, Roberto?
Sure.
Yeah, I got an email with your name has been changed to Robert.
Oh, that's interesting. I don't know why.
Been Americanized. You're no longer a damn Venezuelan. All right.
No, you're gonna say it was like you just like it.
Yes, Roberto. Yeah. Let's find the discriminant here, or the determinant. Gosh, I keep saying the same thing. So I jumped the gun here, and I didn't find a second derivative. So let's classify. Okay. The second order partial derivative, we are looking at the derivative with respect to x of 6xy minus 6x. So we have 6y minus 6. And let's look at the second order partial derivative with respect to y. We are looking at the derivative of 3x squared plus 3y squared minus 6y with respect to y. So this will be 6y minus 6. Notice the unusual case where fxx and fyy, they are exactly the same. And if you do the fxy, well, take the derivative of the left del x with respect to y, get 6x. Take the derivative of the left del y, take the left del y and differentiate with respect to x, it's still 6x. So again, we have the same derivative, second order derivative. fxy equals fyx. And now we are ready to construct the determinant. So it's fxx times fyy minus fxy squared, or in this case 6y minus 6 squared plus or minus 6x squared. Let's write it as 36 y minus 1 squared minus 36x squared. Okay, now we're going to check the determinant for each of the four values that we found. So let's start with d0 of 0, 0. Okay, so what happened here? Well, if x and y both equal 0, then we have 36. 36 times negative 1 squared. So it's 36. 36 is definitely positive. What about fxx? fxx of 0, 0, it's right here. It's negative 6. So it's negative. So what is the conclusion? Relative maximum or minimum? Relative maximum at 0, 0. All right, now we need to check d at 0, 2. So x equals 0, y equals 2. Looking back here, when y equals 2, you have 12 minus 6. That would be 36. And x equals 0. So it's still 36 and still positive. What about fyy at 0, 2? Or fxx at 0, 2? It doesn't matter. We can check either one. Well, fxx and fyy, they are the same anyway. So it will be 12 minus 6. It's equal to 6. It's positive. So we do have a relative minimum at 0, 2. All right. Next is, let's check out what happened at 1, 1. Okay, the determinant will be 36. It will be 0 minus 36, so it's negative 36, and negative gives only one result, which is saddle point. And lastly, D at negative 1 and 1, let's see, we're looking at this expression, so we have, this is still 0, and this is still negative 36, negative 1 squared, so it's another saddle point. So I think it will be interesting to check, to verify these 4 points of this particular curve. So again, off to Maple we go, and we see if we can identify. So here's our function. And again, Roberto cannot see it, and, but you see that I calculated the z value as well. So in addition, when you do it in Maple, you need to provide all 3 variables. So here's the function, and as before, I'll try to stretch it. I'm sorry, here's the graph. Ooh. For some reason my hand starts sliding at one point. Alright, I think you can see it here. This is large enough, isn't it? You can see the point right there. Without changing, what do you think this point? 0, 2. Well, it's a local maximum, so it has to be 0, 2. And you can see that x equals 0. It's I hit something and it changed the color scheme. But what about to see the minimum? It's right here. So I need to go to the rear end of this thing. It's like checking the tail of this animal here. And okay, so here I'm setting up. It's unstable. It's like, but you can see that x equals 0. And this is the z, it's negative 2, but the y will be 2, if you recall. Okay. And the y positive is on this side, so you can see right here that y equals 2. So, and the other 2 saddle points, I think from this view we can see the saddle point, one to the left and one to the right. Okay. So Maple will help you, I guess some 3D technology can help you verify this. Again, if you had to sketch it by hand, that would be quite an undertaking. It would take real artists to be able to sketch it by hand. And I'm not classified as such. All right. Sometimes I manage, but this is really complicated. The way to do it really is pick up one, decide, okay, I'm going to make a 3-dimension to 2-dimension and have a view from, let's say, on this plane. You can see clearly that you have a minimum here and maximum here, but if you go ahead and change it to another view, this is a little bit tougher. You can see that what you had as minimum is actually maximum if you go right here. So this is the view from the top of the Z. You can see all 4 points. All right, enough with this, and let's move on to absolute. Before you go, bring it back. Go back to the class notes. Okay, so let me pause.